Hello, everybody, and welcome to Dr. Bob's Operation Get Good briefing, week number 1. How's it going, everybody? Alright, so we're going to go over the 3 problems that I sent out last week, talk about how I would approach them, and what they mean in reality, and then we'll look at the code that I wrote to solve them, and then I will let you go. Do what you need to do. And this will be sent along with 3 more problems for next week's glorious contest of sorts. Alright, everybody. Let's start off with the first problem. This is called symmetric order. Relatively simple problem. So the idea is, the first thing you want to do is you want to make sure to read the problem and see exactly what's going on. So it says, now when it comes to the contest, a lot of people will say, read every line of the thing. And for a lot of problems, yes, you should do that. But for simple problems, you should probably scan it pretty quick. So in your job at blah, 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 you just finished writing a program whose blah, 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 a list of names in non-descending order by length. So each name is at least as long as the one preceding it. Now, that's an interesting piece of information. Turns out basically irrelevant for the problem. So it says, however, your boss does not like the way the output looks. Instead, wants the output to appear more symmetric, with the shorter strings at the top and bottom and the longer strings in the middle. His rule is that each pair of names belongs on opposite ends of the list, and the first name in the pair is always in the top part of the list. The first example below, Bo and Pat are the first pair, Gene and Kevin are the second pair, etc. So if we look at this example, we've got Bo, Pat, Gene, Kevin, Claude, William, Mary Beth, right there. So it's basically saying, okay, these two, you're going to want them at opposite ends of the list, and Bo will be first, and then Pat will be last, and then Gene will be second, and Kevin will be second to last, and so on. So the input consists of one or more sets of strings, followed by the final line containing the value only 0. This input and output section is usually very important, so that you know exactly what you need to do to start and end the silly thing. And it says, so each set starts with a line containing an integer n, which tells you how many strings are in the set, followed by n strings, 1 per line, sorted in non-descending order by length. Again, almost irrelevant. The idea is, yes, the output should look nice and rounded, but, well, for some of these, but these strings could have been any order, and you just need to put the first one first, and the second one last, and the third one next to first, and the fourth one next to last, and so on and so forth. None of the strings contain spaces. There is at least one, no more than 15 strings per set. Each set is at most 25 characters long. So you could set up an array of length, 15, to hold these strings, and use it that way. Now, you don't actually have to sort that list. You just need to output it in the sorted order. So my approach was to read in the strings into a list, and then add, or go through, starting with the first, and then skipping one every time, output everything on the list, and then at the end, go to the last element that hasn't been output. So if I have an odd number of strings, I've already output the last element, so I need to go to the second to last element. And if I have an even number of strings, I haven't done the last element, so I need to go to the last element. Okay? So, checking out my code here, I wrote this one in Python because it's pretty quick. I actually wrote all of my solutions in Python to begin with. One of them I had to go write in a different language. I'll talk about that in a minute. So, symmetric order. I just grab the integer input, or I grab the first integer from the input, so that's what that does, and I set a value k equal to 1, and then I said while a not equal 0. So it said that the input is going to be terminated by a 0 line, and so I just did that. So then I do this print set whatever, because if you look at the output, it all begins with this set n, where n starts at 1. And so that's what my k is for, is counting what set I'm on, so that I can do set 1, set 2, set 3. Now, I actually submitted this problem once without this line and got wrong answer. I was like, excuse me? Then I figured out what was going on. Okay, this is L. I realize using L as the name for a variable is not great, but it's a list, so I just used L. And this is a fun little line here. So one of the things you can do in Python is what's called a list comprehension. And so you could basically say, I want a list containing this thing for this set of items. So I said for 0 to A, and the way this range works is it's 0, starting at 0 and going to A, but not including A. So it's going to create A things. And I say I want it to grab the input and put it in the list. So it's actually just going to read the input in one line there. And it's really interesting for that set anyway. The next one, Python also has some built-in stuff to let you skip items. So I said for I in range from 0 to A. Once again, that same thing applies. It will do 0, it will not do A. And then 2 here is to skip to the next one. So I print the first one, the third one, the fifth one, though the indices would be 0, 2, and 4, of course. Now, for I in range, this one is interesting. I say A minus 1 minus A mod 2. So, if you recall, I said if I have an odd number of things, if I have an even number of things, then I want to start with the last number. So, the last number is going to be A minus 1. And so in that case, you just want to start with A minus 1. So, and in that case, A mod 2 is 0. So A minus 1 minus 0 is still just A minus 1. Now when you have an odd number, you want to start with the second to last number, which would be A minus 1 minus 1. And since A mod 2 is 1, we get that. So this is just my way of compressing it. We go to minus 1. That means, and again, because the way the range works, minus 1 does not get included in the range, but 0 would. Now, there's actually no way we actually need 0, so I could have used 0 there and it would have worked. Whatever. And this is minus 2. So that tells it to... Oh, sorry about that. Poke the microphone. That tells it to go stepping backwards by 2 instead of forwards by 2. And so this loop is going to print every other string going forward from the first one. This loop is going to print every other string going backwards from the end, either the very last one or the second to last one, depending on the length of the list. Then I grab the next input number, which is the length of the next set, and increment my k, so when I print the set string k, we're done. Fair enough. Alright, next problem. The medium level problem was called honeycomb walk. So you have a bee living in a hexagonal cell. Now, hexagonal cell, that's like this over here. The B here is significantly larger than the B that's being discussed in here because we make sure that the B can only be in one cell at a time. And he's deciding to creep for a walk, so in each step the larva may move to any of the 6 adjacent cells. So like if he's here, he can move to here, 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 or here. And after n steps, you have to end up in the original cell. And so the question is, given the number n, how many different ways can you do that? And it's making sure that n, the way this works, you'll get one number n, you'll get one number that tells you how many test cases there are, and then you'll get 2 more numbers, or you'll get that many numbers to input, and each of those is going to be a length of the path n, and it's constrained between 1 and 14. So first of all, let's just say this: if the path length is 1, which it's allowed to be, if you start at the center and take 1 step, can you end up back at the center? And the answer is no, you can't. With 2, the only ways you end up back at the center are you walk out and you walk right back in. So you can have 1, 2, 3, 4, 5, 6 in a circle. And that's where the 6 comes from. Now there are 90 different ways to get there in 4. And that might seem a little bit counterintuitive. And you can work it out and count it out. One of the things with this problem is you actually could, in theory, just work out the answer for all of these and just have a list that tells you the answer for each one and just have it look it up. That is one thing you could do. I don't recommend it, but you could. So the trick with this, number one, we need some way of representing this hexagonal grid in memory somehow. And some people would like set up a weird data structure in a lot of things. But I prefer to just use a plain old 2-dimensional array. Okay? So let me show you some of the stuff here. Come on. There we go. So, your normal 2-dimensional array is going to look something like this. You're going to have values which are set up like this, and you're going to have plus or minus. You're just going to have an XY coordinate or a row column coordinate, and you might have something like this. You might have a 7x7 array. Well, one thing you can do to this is, without actually changing the structure, you can keep the array as a square array like this, but you can logically treat it like a hex grid by mentally scooching the rows to the right one at a time. So for this center X here, its neighbors are these dots that I'm going to put around it. So it looks like this, but in all actuality, the array is just a 2-dimensional array. So when we actually reference these things, the way we do so looks like this. So you'd be referencing the value in the row above, the value in the row below, the value up and to the right, the value to the right, the value to the left, and the value down and to the left. And so what this ends up doing is, the neighbors of these, as you go out, one area at a time, you actually don't end up using like this whole section, or either the top left corner or the bottom right corner of the entire area to represent it, just because, or as you start building it out anyway. Well, yeah, you do. But there are pieces that will never get used in this. Like this one, depending on how far you go out. So, in this case, what I want is I want an array. I want my array to go ahead and keep track of how many ways there are to reach a given square. Okay? Now, because I'm going to have paths of at most length 14, what I want is my grid to allow me to move 14 in any direction. So I can create a grid that is 29 by 29, and then set the middle square as the starting point. Now, and the initial condition here is that after 0 steps, there's one way to be in the center square, and no way to be anywhere else. Then, what you can do is, to generate the next step, you go through every square in the grid and add together all of the numbers of ways to get to that square from its neighbors. So you look at, for a given square, you look at all of its neighbors and add together those numbers of ways, because that'll be a different way to get there. So, for example, getting back to our notepad example, and I'm going to hex this thing out. So I'm going to show you the calculations for up to 3 steps here. So in the initial step, all of these squares, I'm actually going to set them all to this X, and then I'm going to do a find and replace to make them all zeros. Alright. So we initially have a 0 and we set the center square to 1. So on the next step, we'd have a bunch of zeros, and so for this one, to get its value, we would add the neighbors of the original value in that spot. So that would be 0 and 0 gives us 0. Here we'd have these neighbors, gives us 0. And we get a bunch of zeros around the side. But when we get down here, we see that, say, this spot, which is up here in the original, has a 1 and a bunch of zeros. So in this particular portion of the grid, this would end up having 1. And that makes sense because there's one way to get to that location after one step. Okay, so the next one, like this one, would similarly have a 1, so its corresponding spot in the next list would have a 1, and the same thing goes all the way around the center. Alright, next, so now our next list is going to depend on the previous list. We begin with all of them set to 0. And then we'll go through for each one and add its neighbors. So something like this is going to have a value of 1 at the end of this. This one would have a value of 2 because you can go around this and get 2 different ways. And it makes sense because there's 2 different ways to get there in 2 steps. You can go, say, here, 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 or you can go here, here, here. Right? Okay. So, basically, we would end up having a 1 here, a 2 here, a 1 here, 2 here, wait, that's not a 2, a 1 here, a 2 here, not 22, I don't know where that came from, a 1 here, a 2 here, a 1 here, a 2 here, a 1 here, and a 2 here. Alright. Next, these inner ones, so this one also has a 2 value because there's 2 different ways to get there in 2 steps. You can get there from this one or that one. So all of these have a value of 2. And then the center finally has a value of 6. Because it is surrounded by 1s. Finally, for the last step, let me just go ahead and fill this in and see. I'm not going to explain in too much detail what's going on, but hopefully you'll be able to spot the pattern when I put it in. Okay. So, oh yeah, we need to start these all as zeros. Let me just grab the original. Alright, so on the edge here, we see that this one is going to be a 1. This will be a 3. 3, 1. Then 3, 3, 3, 1 all the way around. So this will be 1, 3, 3, 1, 3, 3, 3, 3, 1, 1, 3, 3, 1, 3, 3, 1, 3, 3. Alright. Now this one has a total of 6 ways to get there. It would be something like 1, 2, 3, 1, 2, 3, 1, 2, 3, and so on. This one would also have a total of 6 ways to get there. 1, 2, 2, 1. So in this ring, we're going to have 6s around the board. Now this is where we're going to have a little bit of an issue, because this will have a total value of 6 plus 2 plus 2 plus 2 plus 2 plus 1 for a grand total of 11. That's going to give us a 2-digit number, so it's going to start looking ugly. That's okay. And then finally, number of ways to get to the center would be 12. 2 plus 2 plus 2 plus 2 plus 2 plus 2. I feel like I might have made a mistake. Because after 4 steps, the answer is supposed to be 90. Oh, yeah, it's not 11. 6 plus 2 plus 2 plus 2 plus 1 is 6 plus 9, which is 15. There we go. And so now you can see that in the next step, when you have 15s around, the result will be a 90 in the middle, and that's why the deal has 90. So let us check out my code solution real quick. This is also a Python submission. So what I did was I created a function. This function will generate the next grid after, given a grid from the previous step, will generate the next grid. So I first create the grid here as a 29 by 29 array. This is probably the most efficient way to do that in Python. You just create a list comprehension containing zeros all 29 times. You could do this one a little faster if you just do like brackets around 0 times 29. But you can't do it for the outside one because then you'll just get references to the same array. So you need something like this. Then I just do a for loop through those. And then this is a little trick I used. I said for k in this array. So this is an array of tuples. And the tuples are like arrays, but they work more like structures. They're just fixed size. And so what I did was I put in -1 0, -1 1, 0 1, 0 -1, 1 0, and 1 -1. Now those are there to indicate where your neighbors should be. So -1 0 is 1 row back and no rows, no columns. -1 1 is no rows, is 1 row back and 1 row over to the right. 0 1 would just be the one to the right. 0 -1 would be the one to the left. And then 1 0 would be the one below. And 1 -1 would be the one down and to the left. And then I just say, okay, I want to add to this new board at position I plus K0. So K, this is a for each loop essentially. It says I'm going to do a thing for every element in this list. So it's saying, okay, first K is going to equal -1 0. Then it's going to equal -1 1. Then it's going to equal 0 1, and so on. So I get the first part of K, which in this case would be -1, and the second part, which would be 0. I add those to I and J, and then I add the current board location to that other location. So I actually did things a little bit reversed in this. In my example that I showed, I created the value at each location by adding up the neighbors from the previous one. What I did here instead was I took each value and added it to its neighbors in the new array. Same effect is achieved, just in a different order. This is a little function that helps make sure that I stay in bounds. There's really no point to it because I'm going to stay in bounds. Then I have an initial board that is also just an array of zeros and things, and then I set the middle portion, 1414, to 1. And then I create a list of results from 0 to 15. And I actually put a result 0 equals 1 here because there's no... because I didn't actually read the problem and see that you couldn't get a 0. But it covers an additional case, so there you go. And I just say, quick for loop running 14 times, get the next board, and then set that value for that equal to the middle count for this value. Then I just say, okay, tell me how many runs there are, and go through, get the runs for each run, grab the input, and then just print the results value steps. So I actually calculate the answers for all of 1 through 14 before I even get the input, because it's pretty easy to do. Alright, last problem, swap to sort. So you are given an array with integers in decreasing order. So that's saying that you theoretically have a list of integers in descending order. They're not actually going to give you that. If you read the input, it doesn't say you first get the list of integers. It doesn't say that. It says you have an array of integers in decreasing order and a list of pairs, A1, B1, A2, B2, and so on. You wish to sort the array in increasing order. So it starts in reverse order, and you want to put it in normal order. Each turn you choose an I can be chosen multiple times, and swap the A-ith element with the B-ith element. So you're given, the idea is you have the length of your list, and then you have some number of pairs that you're allowed to swap. And you're allowed to swap the values at those positions. Okay? Now, this looks like an array sorting problem, but what this actually is a graph theory problem. So now we're going to go to my extremely professional setup here to talk about this one, where I do 10,000 hours in MS Paint. Okay, so the idea is, let's say you have two of these numbers, and you're given the ability to swap those two numbers. Okay? Well, that means that you can definitely swap those two numbers with each other. But then let's say you could also swap, say you've got three numbers, and you're told you can swap one, two, three. Extremely professional. You don't even know. Okay. So you're told you can swap 1 and 2. You're also told you can swap 2 and 3. My contention is you can swap 1 and 3 as well. And the way you do that is first you swap these two, 1 and 2, so that you can get 2 and 1. And you then can swap 1 and 3. and then you can swap 3 and 2. So that essentially gets you the same result as just swapping 1 and 3. Now, you can actually do this with any length of path here. So if we added a fourth, you could swap so we have 1, 2, 3, and 4. You could swap 1 all the way over to the 4, which would then result in would then result in 4, 3, or no, it would result in 2, 3, 4, 1. Then you can take the 4 here and swap it all the way over back to the 2. And so that leaves 2 and 3 in their original positions, and you get 4, 2, 3, 1. So there's a way to swap as long as there is a path of swaps from one number or one location to another. Then you can swap one of them down that path and then swap the other back down the path and leave the rest of the things on the path untouched. Okay? So what that means is essentially these swaps you're creating, they actually form the edges of a graph where each value is a node in the graph. And then to tell if you can do the swap or if you can do the sort, you just need to see if it's possible to swap, say, the first element with the last element, and the second to last element with the second element with the second to last element. So you just need to know if there's a path in this graph from the first to the last, and the second to the second to last, and so on. Another way of saying that is to ask if those numbers are part of the same connected component. Okay? So let's take a look at my solution. This is the one I wrote in Java. So I wrote this in Java. I actually wrote this solution with basically no alterations in Python, and I got timeout errors because Python is slower than Java. So I just wrote it in Java, and it came in under time, no problem. So in order to do this, what I've done is I've created what's called a union find data structure. This is a pretty rare, a pretty obscure data structure that very rarely gets used, but it is actually, for those of you who've taken discrete math, it is the only really efficient way to implement Kruskal's algorithm for minimum spanning trees, and you can also use it here. So the idea is we begin with each element in its own disjoint set, each node. So what I've done is I've created a list of integers called sets, and what this is going to do is it's going to say, okay, for each of these, the set's value should tell me what. So for every set that exists of connected nodes. I want a representative element for that set. And the idea is you're going to be able to use this sets list here to, once you find, once you've connected two sets, or two components, you should be able to find the representative element of that set using this data structure. So it's called union find. It's also called disjoint set data structure. So you begin with every set as its own representative, every node as its own representative element. So I just went through here and just set sets I equal to I in every spot. All right. So now let's go back up here and see what we're doing with union and find. So find says that if the value at data sub k is not k, so data is the same as sets, we're going to pass in sets here. If it's not k, which is the element we're asking about, we're asking what is the representative element for this thing's component. If the data is not k, then that means we are not our own representative element, so we're going to go find the representative element for that element that we just used. But we're also going to set the data k here equal to what gets returned from that. So it's possible that along the way we may have to follow like a fairly long path to find whatever the actual representative element is. But once we've done so, the next time we will just we will have that data set already, so we will skip that entire path to check it. We'll just go right to it. This is what's called path compression, and it is one of the main ways to speed up the union find data structure. So with union, you just say, okay, I want the representative set. Oh, okay, so the idea with union is you pass in two elements, two nodes, and you're then going to say, okay, we're going to take these two elements and the two sets that they're in, we're going to combine them. And that makes sense because when you connect two nodes, you've also connected all the nodes connected to those nodes. Right? So here, we're going to find the two sets, find the representative elements for the two sets which contain those nodes, so I and J. And then if they're not already in the same set, then we're going to set the representative element for set for the I value to the J value. And so that means that the set I belongs to no longer has I set as its representative element, but now has J set. So all the elements in I will eventually need to update their representative element, and they will whenever we call the find on them. And then all we do to check to see if they are connected is just pass in I and J to the data, or we just check to see if, or we find the representative element for I, we find the representative element for J. If they're the same, they're in the same set. So the rest of this is just doing input. So this is kind of an antiquated way of doing input. I know it's what I'm used to. Scanner is usually better for a lot of these things. So if you're used to using scanner, that's fine. But what I did was I just created this buffered reader with an input stream reader, and then I said, okay, grab the first line, and then give me the two values, 5 and 2. You'll also note I declared this to throw an IO exception so that it wouldn't gripe at me when I tried to compile it. One of the things that you'll learn when it comes to competitive programming, especially in a fast environment, is a lot of good coding practice tends to go out the window. It's more important that it works than that it looks good. Anyways, so I grab the number n, which is how many items we have in the list, and I grab how many edges for our graph, or how many swaps, and then I set up my initial sets. Then I go through and read in each pair of elements, or read in each swap, A and B, and then I immediately union the two sets containing A and B. So we added a node to our, adding an edge to our graph, which is going to create, join those two sets into one. And then I go through, for I is 1 to n over 2 plus 1, that is designed to get me the first half of the numbers. I then check to see if I is connected to n plus 1 minus I, and that's to deal with 1 index versus 0 index. And you'll note I actually created the set to be size n plus 1, so it's going to contain values for 1 to n, and it's also got a value for 0, but we're not ever going to use that. Then I just say if it's not connected, if those two are not connected, then it's impossible to sort them, and we print out no and just return, which will end the program. And if we get through all of that, we print out yes, and that's the answer. So, I hope this gave you some insight into the process for some of these problems. I'm going to have 3 more problems this week. Maybe some of them might be a little more on the little more difficult this time. We'll see. Anyways, thanks everybody for bearing with my shenanigans today, and I'll see you later.